Alright, so the last little bit of this involves some more scatter plotting. So we have a table of values that shows wingspan of birds along with their weights, and we're seeing if there is some sort of function that kind of models the two of those two things. The two of those two things. Okay, so this is in the section with power models, so I wonder if this is going to be a power model. If it is, what I'm going to do to check it is not graph x comma y, but graph natural log x comma natural log y, because if that's linear, then the original set of data, the stuff that's in the table, must have been a power function. Moreover, the slope of that thing should be the exponent. So let's put all this information into our calculator right here, and I saved some time by typing it in there ahead of time under L1 and L2. If you had stuff that was already in your calculator in one of these things, you can just scroll up to the title of it, hit clear, and hit enter, and it would clear that whole thing out for you. Okay, so scroll back up to the title of L3 and then type in natural log of, inside the parentheses, second 1 for all the x values, so L1. And then hit enter, and then it populates that for us. It calculates all of the natural logs of all the x values. Now scroll over to L4 and do the same thing. Scroll up to L4, and on its title type in natural log of, and this time we want the y values, which is L2. So second number 2, close those parentheses, hit enter, enter, there we go. And so those are the points that we want to do the scatter plot for. So if I go to second y equals for the stat plot, make sure it's turned on, probably already is, and then change these x lists and y lists to match. The x values need to be from L3 because that's our natural log x, and then the y values need to come from L4, which are the natural log of the y values. So now I'm going to go to zoom, and I'm going to choose number 9 for zoom stat. Voila! It looks pretty close to a straight line. Now it kinks out a little bit up at the top, but we're going to say, hey, that's pretty close to being a power model. So we're going to graph this thing, or find a power model for it. So let's just go. We're going to answer this as yup. Right? So now let's just go through the process of trying to do it by hand, right? So just like I did before, why don't I just take the first point and last point and make myself a power model of this. It's going to be some fantastic decimals on it. Write it in this form, y equals a times x to the b power. Okay, so I'm going to put in 1.9 for x and 0.23, nice, is equal to the y coordinate a times my x value 1.9 raised to the b power. And then for the second one, let's go all the way down to the bottom. Answer is 16.03 is equal to a times 8.4 raised to the b power. Solve the first one for a. So a is equal to 0.23 divided by 1.9 to the b. Sub that in for a in the second equation. So when I do that, 16.03 is equal to a times, well, no. Took the a out and I put 0.23 in its place, divided by 1.9 to the b times 8.4 to the b. Both of the ones that have b as the exponent, let's bring those out in a set of parentheses, so 0.23, and bring the exponent out, so 8.4 divided by 1.9, all this raised to the b. So I'm going to divide by the 0.23, 16.03 divided by 0.23 is equal to 8.4 divided by 1.9, all of this raised to the b power. Now to get the b, I need to do a logarithm. So let's go ahead and take the natural log of both sides of this, and when I do, I'm going to come up here right underneath the eagle. There's an eagle on here, but there's no eagle in the table. Okay, anyway, this is a problem that's straight from the book. I'm going to have b is equal to the natural log of parentheses 16.03 divided by 0.23. All of this divided by the natural log of 8.4 divided by 1.9. Lots of parentheses there. Okay. Pull up the calculator.
Here we go. clear all this thing out and then type in, like you see it, natural log 615.03 divided by 0.23, close those parentheses, divided by natural log again of 8.4 divided by 1.9, close, enter, and I get an exponent about 2.86.
So b is about 2.86. All right. And then for my a value, just plug that back into the a equation. 0.23 over 1.9 to the 2.86 power.
Pull that thing up, and just use the number that's stored in the calculator, right? 0.23 divided by 1.9 raised to the second answer, enter. So 0.3, we'll go with 0.037.
So about 0.037. Write my equation as y equals 0.037 times x to the 2.86 power. Lovely. Lovely, lovely. All right, why did we do all that work, really, guys? We could have just done a power regression on the calculator. And the steps are just like the exponential one, but this time we choose A, power regression. Why don't we try that? Let's see what our calculator gives us.
So this time, go back to stats, scroll over to calc, and I believe that I said it was A, so I'm going to hit alpha A, yeah, power regression right there at the top. L1 is our x values, L2 are y values, and if I wanted to store this, I'm going to use a shortcut this time, which is alpha F4. If you have the new calculator, you can take that shortcut. Let's see what we got. Right there. So our A value is 0.44, our B value, our exponent is 2.87.
How close was that? 2.87. Well, the exponent was pretty close, but the coefficient was a little bit off. Why was it a little bit off? Because remember, we're just using 2 points on our table of values, and the calculator is using all of them, for five of these points, come up with the best fitting model through all of them. So if you have a scatter plot, don't do it by hand. Actually use the calculator to come up with the power regression model from it, right? Okay, well, that pretty much concludes the lesson on writing power and exponential functions. Leave you with one more cartoon, a slide. It's an exponential slide. It says e to the fun. But there's something wrong with that graph, right? Because exponential is supposed to look like the graph right above my head. It's supposed to go like that. Anyway, okay, so here's your assignment. Just a reminder to be working on your John Napier project, because that's going to be due real soon. I think that should be e to the negative fun. Negative fun. No, because negative fun would make an exponential decay function. Let me look back here. This is as if this thing is reflected across the x-axis. That should be negative e to the fun. So you were pretty close, Rowan. You were pretty close. All right, guys, I'll see you back.